Let's talk about Max Planck and the black body radiation problem. A black body is an object that absorbs all electromagnetic radiation and also emits all of it too. One example of this is the sun. The distribution of this radiation is between visible light to UV to infrared, and it all depends on the temperature of the object. The wavelength of the radiation that is emitted with maximum intensity becomes smaller when the temperature increases. This maximum eventually moves into the visible spectrum, where objects reach around 4000 Kelvin, and that's why extremely hot objects glow. It keeps occurring until 5000 Kelvin, where it drops down sharply in the UV spectrum area. The problem is that back then, classical physics had a big issue. Calculations for the long wavelengths worked fine, but shorter wavelengths were not predicted to have a sharp decrease in intensity when approaching the UV spectrum. The math instead said that the intensity of the radiation would continue to increase as the wavelength approached zero, eventually becoming infinity. And obviously this can't be true, because if you did anything like open an oven, you would instantly get blasted with UV radiation and you'd probably die. So this problem was named the ultraviolet catastrophe, as the math broke down when the waves became ultraviolet, as you can see on the graph with the classical theory line. Well, it had already been going up a lot by then, but it became even worse when nearing UV. However, in 1900, Max Planck solved this problem. He was a German theoretical physicist who made many massive contributions to theoretical physics, and he created the basics of quantum theory, which helped reshape our understanding of atomic and subatomic processes. Everyone knows that heat is created when kinetic energy moves to a new location. However, in solids, that kinetic energy is in the form of atomic vibrations instead. These vibrations create the visible light we see in the black body spectrum. At the time, it was generally accepted that vibrational energies of atoms could be any value, but Planck said they had to be discrete from a set of generally accepted values. One example, and he called this quantization. One example of something that is quantized is the charge on particles, as they all have to be a multiple of the elementary charge. Planck then created the equation E equals NHF, E being energy, N being any integer, and H being Planck's constant, and F being frequency of radiation. The N value in this equation results in the energy being quantized, and this is what we call Planck's hypothesis. This means that the energy will be within a set of accepted values, with all other values being rejected. This new quantization allowed for the accurate representation of the distribution of black body radiation at all wavelengths. Even if energy seems to be continuous, in reality, it is quantized with only certain values being accepted. This was how Max Planck solved the ultraviolet catastrophe with his new theory of quantization, which was the basis of modern quantum theory. Now let's talk about wave-particle duality and the double-slit experiment. Back in the 1800s, many people thought physicists like Newton and Maxwell had worked out how almost everything in our universe worked. Newton's laws of motions and Maxwell's electromagnetic radiation theory showed how waves behaved. However, these laws and theories didn't apply to light and subatomic particles such as electrons and neutrons. During Newton's era with classical physics, everything was either a particle and wave, or wave. There was nothing that was both. Particles are things that have mass, charge, and energy. However, waves have things such as frequency, wavelength, and amplitude. They can also interfere with each other, while particles can't really do that. A big difference between particles and waves is how they transfer their energy. A particle transfers their energy in discrete amounts, so for example, if I throw a ball at the wall, it'll hit once, and that's just it. However, waves transfer that energy over a period, so Newton used his own version of the modern double-slit experiment to test light. He believed that the light was made of corpuscles, from his corpuscular theory of light. However, no one could definitively say whether or not light was a wave or particle, and this was a raging debate between Christian Huygens and Isaac Newton. Huygens said that light was made up of a wave, while Newton said that light was made up of these particles. However, for a few decades, Newton's theory was more accepted because of his history as an accomplished physicist. But a few decades later, in 1803, Thomas Young proved that light behaves more like a wave rather than particles. He showed this with his version of the modern double-slit experiment. If it were like Newton's theory, you would expect to see light show up on two spots on the wall instead of what is shown here. Instead, what happened was a lot of small lines of light formed, and we call those fringes. The only reason this should have happened is because some sort of wave interference occurred. Now let's look at a version of this same experiment using electrons over a century later in 1961. Claus Janssen did the same experiment with electrons this time, and he shot a small amount of electrons to the other side. And since we know that electrons are particles, you'd expect to see just two areas with electrons. However, the electrons displayed the exact same behavior as the light, as they formed fringes, as you can see on the right over here. That's the example of the electrons. But since electrons seem to be particles, but also behave like waves in certain scenarios, we can definitively say that electrons behave with wave-particle duality. Now let's talk about the photoelectric effect. The photoelectric effect is defined as when electromagnetic radiation such as light hits a metal and emits electrons. These electrons are called photoelectrons. Now let's look at some light beams. Only sometimes would those light beams emit photoelectrons, and it was really puzzling to scientists because it seemed to be very random. It was later discovered that the ability to emit photoelectrons on impact depended on the frequency of the beam, not the intensity. 5 years after Max Planck created basic quantum theory, Einstein worked with it, and he said that light must be made of quanta he called photons, discrete packets of energy that resembled particles. We can just say that photons are like particles of light. However, photons behave just like waves, with interference, and they don't have mass. Electrons were only ejected when struck by photons with enough energy. Now, how would you know if a photon has enough energy? You would look at the work function. W is equal to E delta V, where E is the elementary charge and delta V is the difference in electric potential. This work function tells you how much energy is required to eject an electron. The unit for this equation is joules or electron volts. If a photon does have enough energy, just one is enough to knock an electron out of the metal. This used Max Planck's equation, E is equal to NHF. But since each photon was just one packet of energy, the equation for energy of a photon became E is equal to HF. When a beam of light has just enough frequency, all the photons would be able to knock electrons out of the material thanks to their energy being high enough. However, if the frequency isn't enough, no matter how many photons hit the electron, it won't be ejected. And this also helped prove how light has properties of wave-particle duality. Now let's do an example question. Iron is being used in a photoelectric effect to experiment. Now calculate the minimum frequency required to emit electrons. Now using this list of work functions for metal, let's just solve. Using the equation born from Einstein's theory of light and Planck's hypothesis, we can solve easily. Now let's just use the work function of iron in joules here, and we can see that the iron's work function is 7.48 times 10 to the negative 19 joules. We just equate that work function to the photon's energy. Since the photon's energy equation is E equals HF, it now becomes HF is equal to 7.48 times 10 to the negative 19 joules, which becomes F equals the frequency is equal to 7.48 times 10 to the negative 19 joules divided by Planck's constant. And since we already know the value of Planck's constant, we can simply substitute and solve, which gives you a frequency of 1.13 times 1.13 times 10 to the 15 hertz. Let's talk about the photon. Now let's talk about photon momentum and the Compton effect. Now, how did we discover that photons have momentum? Well, in 1923, Arthur Hawley Compton was experimenting with the photoelectric effect. However, in the standard experiment, scientists usually shot visible light at metal to displace electrons. Compton decided, he wouldn't do that. He's too cool. So he shot the metal with waves with much higher frequency, X-rays. And then when he shot those X-rays, he discovered that the photons didn't use up all their energy on the electrons within the sheets. The remnants of the high-energy photons became low energy, and then they simply scattered off the sheet, just like the electrons. This was called the Compton effect, and after analyzing the data using brand new special relativity equations from a few decades ago, one or two, the data showed that Compton's experiment showed that the effect conserved energy and momentum, which helped prove that photons do have momentum. And the derivation goes like this. Classic electromagnetic wave theory states that light waves with the energy E also carries momentum, and here's the equation. And since we know that the equation for the energy of the photon is E equals hf, we can substitute that into it to give the momentum of a photon. Photon is equal to Planck's constant times the frequency over the speed of light. Since we know the speed of light, c, is equal to wavelength times frequency, we can also substitute that into the equation. And this results in frequency being cancelled, which gives you a final photon momentum equation of the momentum of a photon is equal to the Planck's constant divided by the wavelength. Now let's talk about the DeBruy wavelength. By the early 1920s, Einstein's photon theory of light was well known to most scientists. However, at the time, only photons were generally accepted to have wave-particle duality. However, in 1924, Louis DeBruy suggested that all classical particles have wave-like properties. Keep in mind that at this time, the electron double-slit experiment had not yet been conducted. This did not stop DeBruy, however, took an educated guess to create his theory based on the behavior of photons. DeBruy knew that the equation P, which is the momentum of the photon, is equal to the Planck's constant divided by the wavelength. So, by working off this equation, he established that since everything has momentum, everything must also have a wavelength. He manipulated the equation to create what we call the DeBruy wavelength, which applies to all classical particles. Later, his hypothesis was verified, as we know, from the electron double-slit experiment. Now let's solve a simple question. In their studies of interference with electrons, Eric and Evan used electrons with a kinetic energy of approximately 1.6 times 10 to the negative 17 joules. The mass of the electron is 9.11 times 10 to the negative 31 kilograms. Now calculate the DeBruy wavelength of these electrons in meters. So we're given the mass of the electron, the energy of the kinetic energy of the electrons, and Planck's constant h, and we're looking for the wavelength. We are also given these equations, and we can solve. And since we are only missing momentum, we can simply use the kinetic energy to solve for the momentum, since momentum is equal to mv, and we're missing v. And since we have the mass, we just need to solve for speed. And it's not velocity because there is no direction associated with the speed. So all we have to do is manipulate the equation so that the speed is isolated. We get this equation, the speed is equal to square root of 2 times the kinetic energy divided by the mass. Now we plug in all the given values. That should result in you having the wavelength of 1.22 times 10 to the negative 10 meters. Now let's talk about the Heisenberg uncertainty principle. The Heisenberg uncertainty principle was created by the German physicist Werner Heisenberg in 1927 when he was working with Niels Bohr in Copenhagen. The principle states that the position of the object and the momentum of the object cannot be measured at the exact same time, and this is because while measuring, the particle will be disrupted and the other measurements will be inaccurate. As you can see, this diagram illustrates what happens. And if you think about it, it makes perfect sense. But just by looking at this diagram, say you wanted to take a photo of the particle that was moving, and you'd be able to find the position, right, and the momentum just by looking at it and doing some calculations. However, you wouldn't be able to tell the momentum because the light wave that illuminated that particle has shifted its course. You now have no idea what direction the particle was originally supposed to go towards. For waves, you would be able to find momentum thanks to DeBruy, but you would have no idea what position the wave is in. And here is his principle quantified, and it states that the uncertainty in position is multiplied by the uncertainty in momentum, and it has to be greater than or equal to Planck's constant divided by 4 pi. Now let's look at some applications of these modern physics in the real world. For example, let's look at the electron microscope. I'll choose to look at the transmission electron microscope, or the TEM. They can magnify specimens up to millions of times. They can do this because electrons have smaller wavelength than light, and the smaller the wavelength, the higher the resolution. First, a specimen is placed within a vacuum chamber inside the tube of the microscope. Now the giant electron gun at the top of the microscope fires electrons towards the specimen, and after firing the electrons, electromagnetic coils and high voltages accelerate those electrons to extremely high speeds. These electrons are then detected by the fluorescent sheet below the specimen being observed. The faster the electrons travel, the smaller the waves, and the more detailed the images that show up. When the electrons reach their maximum speed, they zoom through the specimen and out to the other side, where more coils focus onto the fluorescent sheet to create an image on a screen. And the shorter the wavelength, and the higher the resolution is formed, as stated above, which is why they're fired with such speed. At these speeds, electrons have much shorter wavelengths, and so they're far better than photons for viewing specimens. Here's a comparison between your typical light microscope and an electron microscope, specifically the transmission electron microscope. You can see that the light microscope has a cluster of cells, while the transmission electron microscope has managed to capture just one cell. Many devices also utilize modern physics, such as quantum theory, as electronic devices that contain transistors are only possible because engineers use the wave model of electrons to design these transistors. Without the discovery of the quantum world by those such as Max Planck and Einstein, we wouldn't have achieved so much success as a civilization. Thank you for listening.